Hi and welcome to this video where I'm going to be talking about how you identify strong and weak acids or bases as strong or weak acids and bases using what we call Ka and Kb, which are equilibrium constants, which makes sense since this is an equilibrium topic. Okay, so first off, if we look at the acids, we need to look at the Ka value to figure out whether an acid is strong or weak. If it's not one of those ones that's on the list that I gave you in the last video, if it's one of those ones that's on the list I gave you in the last video, you should be able to identify it on site. But if it's not, then the Ka or Kb will tell you whether it's strong or weak. Now for Ka, what we're talking about there is the equilibrium constant for the acid's dissociation with water. Okay, simply put, K is always an equilibrium constant. So just to recall, as an equilibrium constant, it is a constant value at standard conditions. And you can typically look these up in data tables and textbooks. So if we consider any generic acid, we're going to call it HA, where H is the hydrogen ion and A is the anion. Okay. That acid, assuming it's a weak acid, is going to, well, even if it's a strong acid, but I've done it with an equilibrium error, so we're going to think of it as a weak acid, will react with water to donate its proton, forming an anion. We can write an equilibrium constant for this reaction, where Ka, which is the equilibrium constant for an acid, is equal to the concentration of the hydronium ion times the concentration of whatever anion we have, divided by the concentration of the undissociated acid. Remembering, of course, that we don't include water because water is a pure liquid and has a constant concentration. Now this equation, if you think about it really carefully, this equation can be used in lots and lots of ways, and this is actually going to be the basis of most of the calculations we're going to do in the rest of this topic. So the value of Ka can tell us whether or not an acid is strong or weak. If we have a strong acid, then because it is heavily product favoured and a strong acid, it's all going to, the reaction is going to go to completion, then Ka is going to be significantly larger than 1. Most of what we're going to deal with in this topic are weak acids where the Kas are significantly less than 1. So typical values for Ka would be around something times 10 to the minus 4 or 10 to the minus 5. So 0.0000 something or other. Okay, so those would be typical values for a weak acid, or for a weak acid. Now we can do something very, very similar with strong and weak bases. And we have, again, an equilibrium constant, which in this case we call Kb. Chemists are very imaginative, so Ka for an acid, Kb for a base. Okay, so if we think about the reaction of a base with water, there are two. Now this one here is really a strong base, so sodium hydroxide, potassium hydroxide, possibly lithium hydroxide. Okay, if it's a hydroxide, it's going to be in this kind of format, where the base reacts to form a cation and hydroxide ions. You do occasionally get that for an insoluble hydroxide as well, which kind of makes it a weak base. But the more common ones that we're going to deal with, things like amines and ammonia, are going to accept a proton from water. And so if we look at that second equation in particular, we can write an equilibrium constant expression for that, which we call Kb, as such. So the two products divided by the concentration of the undissociated base. And as with our acids, the size of that value will tell us if the base is strong or weak. A strong base will have a very large value for Kb, and a weak base will have a small value for Kb. Now, if we tie the information about Ka and Kb together with what we know about acids and weak acids and conjugate bases, or weak bases and conjugate acids, then actually there's a lot of things we can put together. Now, just a quick word on notation first. Okay, so Ka is the equilibrium constant for an acid and Kb is for a base. But quite often, these numbers tend to be fairly ugly, just like hydronium ion and hydroxide ion concentrations. So just like that, we can make the numbers easier to work with by converting our Ka into a pKa or our Kb into a pKb. Okay, so just like we turn our hydronium ion concentration into a pH, it's exactly the same calculation. So pKa is negative log Ka, or pKb is negative log Kb, and of course you can reverse that calculation as well. So because these are negative logs, if the pKa ends up quite small, like less than 1, or a negative number, then the acid is strong, and if the pKa is greater than 1, then the acid is weak. So typical values for a weak acid would have a pKa of between 3.5 and 6. That would be pretty typical. That will cover your range from methanoic acid through to ammonium. Okay, and of course the same thing kind of can be said for Kbs. I can turn them into pKb. So like I said, acids and conjugate bases go together. And so the Ka for an acid and the Kb for the conjugate base of that acid are related. And we can look at them in this way, where the Ka times the Kb is equal to the Kw, which, if you'll recall from level 2, Kw is the dissociation of water, and at 25 degrees C and 1 atmosphere of pressure, that number is equal to 1 times 10 to the minus 14. So if we know Ka, we can calculate Kb, and vice versa. And we can also take the negative log of all of these pieces of information, and so actually pKa plus pKb will give us 14. Now that allows us to manipulate our numbers quite a lot, and I really recommend that you think about this. We're going to do a lot of calculations, and I've summarized some conversions on this diagram. Now, you don't have to memorize this. Some people love it and some people hate it. If you hate it, please ignore it, okay? But if you like it, if it's something that makes sense to you, then please do think about how this connects. And I'm going to do a very similar one with pH and H3O plus and OH and POH. Because actually, from this you can kind of figure out how to get anywhere you want to be. For example, if you're given a pKa, pKa for an acid, and actually it's a base and you want to use it Kb in a calculation, you can convert from pKa to Kb following one of these paths, either turning it into pKb and then into Kb, or converting it into Ka and then Kb. And the formulas are all there. The more practice you have at this, the easier it becomes, and I'm going to work through some examples as we get into some calculations later, so I hope you'll find that useful. But I wanted to just show you this right now because it kind of relates. Now this is only for an acid and its conjugate base, not for any acid and base, right? But always for an acid and its conjugate base. Right, I shall see you in the next video where we're going to start looking at some calculations.